Now let's look at some Karnaugh maps for functions which have 3 variables. This truth table has 3 inputs, or to put it another way, 3 variables. To construct a 3-variable Karnaugh map, we could start by placing possible input values for one of them, in this example A, in the column headings like this. Now we can have one row for each combination of values for the inputs B and C, starting with B equals 0 and C equals 0. Then B equals 0 and C equals 1. Now B equals 1 and C equals 1. And finally, B equals 1 and C equals 0. We now have all of the possible combinations of inputs B and C included. You can see that as you scan down the row labels, each pair of input values for B and C differs from the next or the previous pair by only 1 bit. These are not sequential binary numbers. This is quite deliberate. Indeed, it's an essential aspect of the construction of a K-map with 3 or more variables. Okay, now we can transfer data from the truth table to the K-map by using the input values as coordinates for the placement of output values. The K-map is now fully populated and ready for use. When we look for the largest possible groups of 1s, we can see 2 overlapping groups here. There are some rules we must obey when it comes to grouping. One of these is that a group must be a horizontal or a vertical rectangle, or a square. More about these rules later. Suffice to say for now, we've obeyed them. Upon inspection, we can see that the tall vertical block of 1s always matches the input value of A. So this expression includes A. And if you look carefully, you can see that the other block of 1s always matches the input value B. Hence, this K-map represents the expression A or B. We could have constructed a different looking K-map from the same truth table. Both of these K-maps contain exactly the same information, but one of them is turned through 90 degrees. We've also combined the input values differently in the alternative version. This time, the input values for A and B are paired up and are now acting as row headings. Again, you can see that as you scan across these row headings, each pair of input values differs from the next or the previous pair by only 1 bit. Looking for the largest possible group of 1s, the uninitiated might decide that this is a candidate. But this breaks one of the rules. A group cannot contain 6 1s. It can only contain 1, 2, 4, or 8 1s, or to put it more generally, 2 to the power n 1s. But we can have 2 overlapping groups of 4. This is correct. Upon inspection, the 1s in the group on the left always match the input value B, and the 1s in the group on the right always match the input value A. So we arrive at B or A. The horizontally arranged version of the same K-map that we saw before has given us essentially the same result. From the vertically arranged version, we arrived at the expression A or B. And in case you were wondering, if we had created 2 groups like this, we would still arrive at the same conclusion, that this K-map represents the expression B or A. And 2 groups like this would yield the same result. But it's always best to create groups as large as possible. Here's a different example. Let's see what we can make of it. We have 2 groups of 1s that obey the rules we've looked at so far. The 1s in the long horizontal group are always the opposite of C. That is, they are not C. And the 1s in the square block always match the value of input A. Hence, we have the expression not C or A. This example illustrates something we haven't seen yet. We have a small group of 1s here. We can see that these 1s correspond to an input value of 1 for A, And they also correspond to an input value of 1 for b. So this K-map represents the function a and b. Notice that when we're describing a single group of ones that's dependent on different input values, we use the AND operator to describe the relationship between the inputs. On the other hand, we've already seen that we use the OR operator to describe the relationship between different inputs in different groups of ones. This example illustrates a new rule for grouping ones together. We have a single group of 4 ones that wraps around the table. Imagine the table has been rolled up into a tube so that the top and bottom rows are now adjacent to each other. This type of group is allowed. We can see that where there are ones, sometimes A is 0 and sometimes it's 1. So the output of the circuit that this K-map represents is independent of A. Also, where there are ones, sometimes B is 0 and sometimes it's 1. So the output of the circuit that this K-map represents is also independent of B. But where there are ones, the value of C is always 0, the opposite of the output. So this K-map represents the function not C. Here's another example. Here we have another group of ones that wrap around the table. Where there are ones, A is always 1. And where there are ones, the value of C is always 0. But the output is independent of B. Remember, because of the table wrapping rule, there is only one group of ones here, so this K-map represents A and not C. To finish then, here's a summary of the rules for identifying groups in a K-map. A group must only contain ones, no zeros. A group can only be horizontal or vertical, not diagonal. A group must contain 2 to the power n ones, for example 1, 2, 4, 8. Each group should be as large as possible. Groups can overlap, and groups can wrap around a table. Every one must be in at least one group. And finally, there should be as few groups as possible.